So this is the chapter 23 homework. There are two conceptual questions and several problems. So for the first one, it was gave you this graph. Hey, thanks, Scanware. And three resistors, and it was basically asking you to rank the resistances. So essentially, if we have a steeper slope, we have a greater change in voltage, which is a change in potential, and therefore that means we have a greater resistance. So I get R3 is greater than 1, and then is greater than R2. The current's got to be the same everywhere through here, so it makes sense that I have the greatest voltage drop with the greatest resistance, since V equals I times R. For question 9, basically was asking you to compare these potentials. So the change in potential is the same from C to D as it is from A to B, as long as these batteries have the same potential. So all of the voltage is used up across the resistors, whether there's only one, whether there's three, or there's a bunch of them. So here, the current through I1 would be greater than the current through I2 or I3. Since if the resistors are identical, I have only one resistance here, three resistances here. So the current through I2 and I3 would equal each other, but be less than the current through I1. And those are both series circuits. For the problems, for problem 9, it gave you a scenario. So it was something like this, and you were to assume the starting position was at the lower left-hand corner, you were moving clockwise. So if I go from 2 volts down to 0, that means the 0 is approaching the negative terminal of the battery, which is the lowest potential of the circuit. Across the battery, you go up for the entire voltage, which will look like 6 volts to me. And then across the 2 ohm resistor, we end up going down 4 ohms. So essentially, I could figure out these different resistances by knowing how the potential changed. So if the current is the same through here as through here, twice the voltage would be used across this as this. For P21, there are 3 1 kilo ohm resistors, and it's asking for the number of different arrangements you can have. I could have one of them like this, which is 3 in series, so it's 3,000 ohms. I could have 3 in parallel, that's 333 ohms. I could have 2 in, 2 in parallel with 1 in series, and that becomes 1,500 ohms. And here I have 2 in series and 1 in parallel with all of that, and that would be 667 ohms. So 1 over 1,000 plus 1 over 2,000 equals 1 over the total resistance. For problem 22, the key thing here is it showed you had 7.5 volts. Since these batteries are facing the same orientation, that means they add up. If they were facing opposite orientations, you'd subtract one off from the other. So if the batteries provide 7.5 volts, and yet we use 5.5 volts across these resistors, that means I have 2 volts to use across this. So 2 volts equals I, the current, times R, which is 150 ohms. So I rearrange that and get a current of 0.0133 amps. And the current's the same everywhere in a series circuit. For P30, we went over in class, and I told you I had a lot of redrawings to do, so I think you can sort of see that here. In order to simplify this circuit, oh, and I forgot to write that back there, because I boogered up my math initially, so give me a second here. 6 ohms right in the middle. There we go. So 6 ohms there. And I show you how I go simplify from first to second to third to fourth to fifth to sixth. Again, I'm combining these resistors as I go to get a single equivalent resistance. Finally, I get a single resistor of 4.4 ohms. That's how I come up with 1.35 amps. You cannot do this in one big step. For P33, I was asking you to find the voltage and current through each resistor. So I labeled them A, B, C, D. I don't know why I did that because they were all different. So I stopped doing that notation earlier or later. So I can redraw it like this: 3 ohms in front before the current splits, then 4, 48, and 16. So these 3 branches come out to 3 total ohms. So my simplified circuit looks like this. So I have 2 amps, and so therefore I've got 2 amps and 6 volts across the 3 ohm resistor here. Then, if I can think of this as an equivalent 3 ohm resistor, that means that I would have the equivalent of 2 full amps going through it as well. So that's 6 volts across this component. And that means it's 6 volts across each of these 3 branches, because however the current splits up, B, C, or D, you've got to use up the remaining 6 volts. So to find the current, I would take that 6 volts in this branch and divide it by the 4 ohms. That gives me 1.5 amps. 6 volts divided by 48 ohms. 6 volts divided by 16 ohms. Down here, this is tough and sneaky. So I'm not surprised people asked about it in class. Again, we went over it a lot. But basically, this is sort of a tricky parallel resistor. A little bit of a short circuit there in this part and this part, which is what turns it into basically 3 resistors in parallel with each other. Just sneaky. I really had to look at that. So this goes through the total resistance. This really isn't exactly like this, because you see this is kind of a short circuit, but it's a short circuit that gives you a 10 ohm branch. So I had 3 total amps in the circuit, 1 amp through each of these resistors. I've drawn the direction they're going up here. So I think the key thing is to note that at point 1 and point 3 you're at 10 volts potential still, because there's no resistance between those spots and the spot where we know it's 10 volts. And for points 2 and 4, those are at 0 volts, because there's no resistance between those spots and the spot with 0 volts. For problem 72, I have 2 24 ohm resistors, so I'll put one as an asterisk. It's basically asking you to solve for the current resistance through each of them. So first thing I did is simplify this. That becomes a 6 ohm. 6 and 6 is 12. 4 in series with a 12 and a 24, which are in parallel with each other. They become an 8. So 4 plus 8 would equal 12 ohms. So that's my total resistance. Total current is 2 amps. So once I know my total current, that's the current going through the 4 ohm resistor, 2 times 4 is 8 volts. That means I have 8 volts left to use for the rest of the trip. So, that means I have 16 volts to use for the rest of the trip. So in this particular case, if I go this outer branch, this outer path, then only the 24 ohm resistor with the asterisk is in that path. So therefore, almost 16 volts must be used across it. 16 volts divided by that specific resistance of 0.24 ohms gives me 0.67 amps. For this one, this is the 6 ohm resistor here. I can think of this particular branch, which is a 12 ohm branch. I know that I've got 16 volts left to use because I used 8 volts across the 4 ohm resistor. So there's other ways you can figure that out also, but 16 volts across this divided by 12 ohms gives me 1.33 amps. So there's actually 1.33 amps going through this entire branch. That means there's 1.33 amps going through the 6 ohm resistor, which is what I've got here. The other way you could figure that out is if you have 2 amps total, and you've already figured out you have 0.67 amps through the outer 24 ohm resistor, you have 1.33 amps left. Multiply that by the 6 ohms, you get 8 volts. So now for this part, here and here, I know that if I've used 8 volts here, 8 volts here, then either path the current takes, I would have to use the remaining 8 volts. You could also think of it as that if you use 16 volts across this outer 24 ohm resistor, and we use 8 volts across the 6, then I've got 16 to use. I've already used 8, pardon me, I don't know if I said that correctly before, so I have 8 volts left. So there's a bunch of ways you could think about that. I end up showing that it splits. If I have 8 volts divided by 8 ohms, that's 1 amp. 8 volts divided by 24 ohms, that's 0.33 amps. That should equal the total going through the 6 ohm resistor, and it does. So hopefully that makes sense. And hopefully you do well on your circuitry quiz.